نحمده ونصلي على رسوله الكريم أما بعد فأعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. Today's topic of discussion is Pearson's correlation. I am Dr. Fatma Jalal Chaudhary and I am an MPhil scholar here with you, and I'm going to present the very topic under the kind supervision of Professor Dr. Sarah Afzal, who is our dean. Now, what's the agenda for today's discussion? I have highlighted some of the points. Basically, we'll try to have an introduction towards what's the Pearson's correlation, what are the properties, Pearson's correlation, significant historical changes, correlation coefficient, uses and implications, along with some numerical protocols. What is the value of R and its significance? How are we going to interpret it, and what are the uses of it? Recent advances in the same topic and MCQ session and a key takeaway lesson for us. What are the objectives for today's discussion? At the end of the presentations, the participants, I hope, would be able to understand and identify Pearson's correlation and Pearson's coefficient correlation, its major implications and properties, what are the major calculations which we can do through the same topic, and how are we going to interpret through the SPSS. Now, a brief introduction. In statistics, the Pearson's correlation, or PCCI, is a correlation coefficient that measures the linear correlation between two sets of data. It is the ratio between the covariance of two variables and the product of their standard deviation. Thus, it is essentially a normalized measurement of the covariance. Such that the results always have a value between -1 and 1, so that R can be interpreted between -1, 0, and 1. As with the covariance itself, the measure can only reflect a linear correlation of variables, and it ignores many other types of relationships or correlations. So, as with the covariance itself, the measure can only reflect a linear correlation of variables, as we have discussed, and it would be through scatter plot either, or through the line diagrams, which we would be discussing in the further coming section. And it ignores many other types of relationships or correlations which are either occurring through chance or covariantly. As a simple example, one would expect the age and height of a sample of children from a school to have a Pearson's correlation coefficient significantly greater than 0, but less than 1, as 1 would represent an unrealistically perfect correlation. So these are the examples of some of the scatter diagrams which are showing us with the different values of correlation coefficient, which is being depicted here as a small p. So in a case where we have -1 correlation, we'll be seeing a line which is inclined towards basically increasing from the y-axis and along so the x-axis. But the points here are depicting that it's a negative correlation. Similar is the case here in the next diagram, where we can where we can see that one is either less than p or p is less than 0. In both the cases, we are going to get a negative sort of correlation. So in the cases where there is p which is either greater than 0 or is coming towards +1, there would be a positive correlation and a scatter plot diagram, and same with the cases here. Here where the p is equal to 0, we can't get a significant sort of line for a scatter data. And same is the case here. Here we can observe that there are 1 to -1 or -1 sort of settings for a scatter plot, and here is the zero thing. And all of these cases are basically different correlation coefficient values. So, what is the naming and history behind Pearson's correlation? It was basically developed by Carl Pearson from a related idea introduced by Francis Galton in the 1880s, and for which the mathematical formula was derived and published by Auguste Bravais in 1844. The naming of the coefficient is thus an example of Stigler's law, which would be basically be governing whole of this equation. So what was the motivation, intuition, and derivation for using the correlation coefficient? The correlation coefficient can be derived by considering the cosine of the angle between the 2 points, representing the two sets of x and y coordinate data. This expression is therefore a number between -1 and 1 and is equal to unity when all the points lie on a straight line. So what is the definition? Pearson's correlation coefficient is the covariance of the two variables, which is divided by the product of their standard deviations. As we have discussed earlier, the form of the definition involves the product movement, that is the mean, the first movement between the origin of the product of the mean adjusted random variable. Hence, the modifier product moment in the name is used. So we have basically two sets in which we are going to be dealing with the coefficient correlation in a population or in a sum. So for a population from which we are going to derive a sample, how are we going to express the Pearson's correlation coefficient? So this is a simple example quoted here. Pearson's correlation coefficient when applied to a population is commonly represented by the Greek letter P or rho and may be referred to as the population correlation coefficient or the population Pearson's correlation coefficient. Given a pair of random variables, like for example, x and y, height and weight, x represented by height and y represented by weight, the formula for P would be Pxi, covariance of both the product xi and divided by sigma x and sigma y, which are the standard deviation, where COV is the covariance and this is the other formula. The formula for covariance xy can be expressed in terms of mean and expectations as likely this equation. But these are not that sort of complex, you can easily remember. So what is the formula for P? The formula for P can be written also as like this, expressed here, where mu x is the mean of x and mu y is the mean of y. E is the expectation or expected outcome for a population. So another expression for the population mean can be written as this equation given here. So for a sample, how are we going to determine the Pearson's correlation coefficient when applied to a sample? It's commonly represented by R, X, Y, or simply R, and may be referred to as the sample correlation coefficient or the sample Pearson's correlation coefficient. We can, by this very equation, obtain a formula for Rxy by substituting the estimates of the covariances and variances based on the sample into the formula, which is given here. Given the paired data x1 or y1, or it would be linking on to xn or yn, could involve any of the quantities here consisting of n pairs. Rxy is defined as this is the equation. Basically, this is the summation sign and this is the sign for the under root. So for another expression is for the jointly Gaussian distribution. So we have two basic expressions which are for the population or sample either. So in the cases where there are more complex sort of calculations there, we are going to use the jointly Gaussian distribution. For if xy is jointly Gaussian between 0 and variance, which is the sigma, then sigma would be represented as here. And in this very equation in which we are going to have the distributions, we have some practical issues. Under heavy noise conditions, extracting the correlation coefficient between the two sets of stochastic variables is non-retrievable. That means it can't be retrieved back once we are done with the calculation. In particular, their canonical correlation analysis reports degraded correlation values due to the heavy noise contributions. A generalization of the approach is given elsewhere. In the case of missing data, Guerin derived the maximum likelihood estimator for the same jointly Gaussian distributor and to overcome the heavy noise condition. Some distributions, for example, stable distributions other than a normal distribution do not have a defined variance. So what are the mathematical properties for a Pearson's population correlation? The values for both the sample and population Pearson's correlation coefficients are on or between -1 and 1, including 0. So correlations equal to +1 or -1 corresponds to data points lying exactly on a line in the case of the sample correlation, or to a bivariate distribution entirely supported on a line in the case of the population correlation. So the Pearson's correlation coefficient is symmetric covariance for the xy and covariance for the y-axis. So a key mathematical property of the Pearson's correlation coefficient is that it is invariant under separate conditions or changes in location and scale in the two variables. That is, we may transform x to a plus bx and transform y to c plus dy, where a, b, c, and d are constants with b, d equals or more than to 0 without changing the correlation coefficient. This holds for both the population and sample Pearson correlation coefficients. More general linear transformations do change the correlation. For this, we have to look for the decorrelation of n random variables for an application of this very property. So how are we going to interpret the correlation coefficient? The correlation coefficient, as we have discussed earlier, would be ranging from -1 to 1. So an absolute value of exactly 1 implies that a linear equation describes the relationship between x and y perfectly with all data points lying on a line. So the correlation sign is determined by the regression slope. It's a value of +1 that implies that all data points lie on a line for which y increases and x increases. Whereas a value of -1 implies a line where y increases while x decreases. So a value of 0 implies that there is no linear dependency between the variables. So this is basically the regression lines where you can see it's a y, a gxx, which is represented through the red color, and x represented by gy into y, which is represented by the blue color. So this is the covariance and the variance which are coinciding at a point where intersection could be drawn. This is the x-axis and this is the y-axis. So along the y-axis, we can at any point have the value of y bar, and along the x-axis, we can have the value of x bar. So variance wherever the red line coincides with the blue line and a tangent is drawn, we are going to get the exact point where we can find the value of x. And this basic expression is the key point behind all of the scatter plot diagrams and the Pearson's correlation coefficient and elsewhere as well. More generally, x I minus x into y I minus y is positive if and only if x I and y I lie on the same side of their respective mean. That means if one is lying on the positive side, the other variable should also be lying on the positive side. Thus, the correlation coefficient is positive if xi and yi tend to be simultaneously greater than or simultaneously less than their respective means. The correlation coefficient is negative or anti-correlation if xi and yi tend to lie on opposite sides of their respective means. Moreover, the stronger either tendency is, the larger is the absolute value of the correlation coefficient. This is the line which we have discussed. Now, what is the geometric interpretation which we are concerned with? For all of the uncentered data, there is a relation between the correlation coefficient and the angle sigma between the two regression lines. Regression lines are basically the same lines which we have discussed in blue and red, where y is equal to gx and x is equal to gy into y of time by regressing y on x on y respectively. For the centered data, that is the data which have been shifted by the sample means of the respective variables, so as to have an average of 0 for each variable, The correlation coefficient can also be viewed as the cosine of the angle sigma between the two observed vectors in the n-dimensional space for n observations of each variable. So numerically, if the same thing is being explained, it would be expressed as suppose these same 5 countries in the same order, like 1, 2, 3, are found to have 11%, 12%, 13%, 15%, and 18% poverty. Then let X and Y be ordered 5-element vectors containing the above data X 1, 2, 3, 5, and 8, and Y 0.11, 0.12, 0.13, 0.15, and 0.18. By the usual procedure for finding the angle sigma between the two vectors, which is the dot product, the uncentered correlation coefficient is cosine of the angle x dot y divided by x bars and y bars. This is a simple expression for this, and cosine angle would be 0.9. So how are we going to interpret then this result to determine the size of the correlation? Now, several authors have offered the guidelines for the interpretation of a correlation coefficient. However, all such criteria are in some ways arbitrary. The interpretation of a correlation coefficient basically depends on the context and purposes. A correlation of 0.8, for example, we are going to have two variables and going to check their relationship. We are going to first check that either we need the correlation coefficient, as in if that lies in the regression analysis, then only we can interpret the correlation coefficient. So a correlation of 0.8 may be very low if one is verifying a physical law using high quality instruments, but may be regarded as very high in the social sciences, where there may be a greater contribution from complicating factors. So what is the usefulness for all of this R values and other things? As we can see a graph here, it's the absolute value of Pearson's correlation starting from 0 going up to 1. So this is the prediction interval reduction factor, which is again 0 to 1. So here we can see an upward slope going along the x-axis and following to the y-axis. This figure gives a sense of how the usefulness of a Pearson's correlation for predicting values varies with its magnitude. Given jointly normal x and y, with correlation p 1 minus under root 1 minus p square, plotted here as a function of p, is the factor by which a given prediction intervals for y may be reduced. For example, if we are going to interpret it at 0.05, so we are going to draw a tangent here. So it might be reduced here. Given the corresponding value of x. For example, if p is equal to 0.5, then 95% prediction interval of y along the x will be about 13% smaller than the 95% prediction interval of. So how are we going to get the inferences about all of these things? Statistical inference based on the Pearson's correlation coefficient often focuses on one of the following two aims. One aim is test the null hypothesis, that the true correlation coefficient P is equal to 0 based on the value of the sample correlation coefficient, which is R. The other aim is to derive a confidence interval that on repeated sampling has a given probability of containing P every time. Standard error, how are we going to calculate it? If x and y are random variables with a simple linear relationship between them and additive normal noise, this one is the given equation, then a standard error associated to the correlation is expressed as this equation, where R is the correlation and N is the sample size. So testing while using the student's t distribution test for this critical values of Pearson's correlation coefficient that must be exceeded to be considered significantly non-zero at the 0.005 level. So this is the sample size, and this is the critical correlation where we can see it's increasing. Alpha value kept here constant at 0.05. It's one-tailed in blue and two-tailed in red. So for pairs from an uncorrelated bivariate normal distribution, the sampling distribution of the standardized Pearson's correlation coefficient follows a student's t distribution with degrees of freedom n minus 2. specifically because it's a bivariate. If the underlying variables have a bivariate normal distribution, the variable could be expressed here like this. So have a student C distribution in the null case where it is considered as 0. So in least square regression analysis, where the value of R is interpreted, what is the use? The square of the sample correlation coefficient is typically denoted R square and is a special case of the coefficient of determination. In this case, it estimates the fraction of the variance in Y that is explained by X in a simple linear regression. So if we have the observed data sets Y1 to Yn and a fitted data set, it is by var1 to by Vn, then as starting point, the total variation in the yi around their average value can be decomposed as follows or decompressed as follows, where are the fitted values from the regression analysis. This can be rearranged to give this equation where 1 stands equal to all of these summation. The two summands above are the fraction of the variance in y. Summands are mean summation that is explained by x right and that is unexplained by x left. So sensitivity to the data distribution, how are we going to have a look at the properties which we would be discussing with the Pearson correlation. So how is the existence going to be explained? The population Pearson correlation coefficient is defined in terms of moments. Therefore, it exists only for bivariate probability distribution for which the population covariance is defined and the marginal population variances are defined and are non-zero. So, and these are also some of the for the habitat. Now, how are we going to express it for the sample size? If the sample size is moderate or large and the population is normal, then in the case of a bivariate normal distribution, the sample correlation coefficient is the maximum likelihood estimate of the population correlation coefficient. And it's asymptomatically unbiased and efficient, which roughly means that it is impossible to construct a more accurate estimate than the sample correlation coefficient. So how are we going to look at the robustness of the calculations or the results given here? Most commonly used statistics, the sample statistics is not that robust. So its value can be misleading if outliers are present. Specifically, PMCC is neither distributionally robust nor outlier resistant. So inspection of the scatter plot between X and Y, and this is an example of which being quoted here, will typically reveal a situation where lack of robustness might be an issue where we can't get a straight line out of it. So what are the variants for the same correlation coefficient? There is adjusted correlation coefficient. Sample correlation coefficient R is not an unbiased estimate of P. For data, we follow bivariate normal distributions. This is the adjusted correlation coefficient, which is expressed here as R adjusted. Weighted correlation coefficient is another variate in which weighted means weighted covariances are firstly calculated and out of which we are going to calculate the weighted correlation between the two weighted correlation. So what are the software implementations for the same R's value or the correlation coefficient? So our statistic based package implements a correlation coefficient where covariance or with the p-value with the SkyPy Python library also uses this thing with the Pearson's R, XY, the Pandas and Polar's Python libraries implement the Pearson correlation coefficient as a default option for methods. This is the expression given here. So Wolfram Mathematica, the Boost C++ library also uses this function. Excel has an inbuilt correlation array2 function for calculating the Pearson's correlation function. These are inbuilt functions basically for all of these softwares given. So what are the recent advances? Here we are going to discuss some of the journal articles and book chapters. So this is a book chapter in which Jules R. J. Berman and thinks about the data simplification. So Pearson's correlation for two objects with paired attributes sums the product of their differences from their object means and divides the sum by the product of their required differences from the object means. It is expressed as here. So you may notice that with the Pearson's correlation is parametric in the sense that it relies heavily on the mean parameter for the two objects. This means that Pearson's correlation might have higher validity for a normal distribution with a centered mean Then for a distribution that is not normally distributed, such as ZPF distribution. So Python SPICY module offers a Pearson function. In addition to computing Pearson's correlation, the SCIP function produces a two-tailed p-value which provides some indications of the likelihood for the two uncorrelated objects. So this is another review article, journal Front Opinion in Systems Biology, Gene Regulatory Network Inference in Single Gene Biology, Pearson's correlation, a well-established statistic for calculating the association between the two variables, has been applied to measure co-expressions of the TFs and target genes in both RNA sequence and scRNA sequence datasets. So being symmetric in its arguments, this correlation does not predict the directionality of the regulatory interaction. This is the Pearson's correlation test. How are we going to interpret it? Biostatistics Manual for Health Research. Spearman's correlation or Spearman's RHO can also be applied or as an alternative for the non-parametric sequence. So measuring the normality test through the Shapiro-Wilks test or Pearson correlation test, are we going to calculate it through the SPSS and apply it? So this is an example quoted here. For example, we want to know the association between vitamin D level and parathormone levels available at 6 vitamin D PTH file. The research question and hypothesis are: research question is vitamin D level correlates with PTH levels. The hypothesis is H0, there is no correlation between vitamin D and PTH, and alternate is there is correlation between vitamin D and PTH level. So what are the steps which are going to be followed? These are the files which are coming under your way. This is a scatter plot which we are going to get at the end of the discussion, and results. How are we going to interpret it? They are also given with a p-value less than 0.001. So MCQs session, MCQ number 1, a researcher finds a Pearson's correlation coefficient of R is equal to 0.84 between hours of social media use and GPA. What can the researcher reasonably conclude? More social media use causes lower GPA. There is a strong negative linear relationship between social media and use and GPA. There is weak positive relationship between social media use and GPA. Or there is no relationship between social media use and GPA, and correlation is very ambiguous. So what could be the answer? B. Yeah, answer is B. There is a strong
Alpha.
yeah, it's B. There is a negative, strong linear relationship between social media use and GPA. R is minus point. MCQ number 2, two variables X and Y have a Pearson's correlation coefficient of R is equal to 0. What does this imply? X and Y are not related in any way. X and Y have no linear relationship. X causes Y. X and Y are inversely related. X and Y cannot be correlated or interpreted. So what are your thoughts? Yeah, answer is B. B. X and Y have no linear relationship as the R value is 0.
Okay.
So MCQ number 3, a scatter plot shows a clear non-linear pattern, yet the Pearson correlation coefficient is close to 0. What is the best interpretation? Two variables are not related. Pearson correlation is inappropriate due to the non-linear relationship. The variables have no variance. The sample size is too small, or the variables are inversely related. Clear non-linear pattern, which is close to 0.
B.
Okay. Answer is B. Pearson's correlation is inappropriate due to the non-linear relationship, as we discussed. MCQ number 4, which of the following changes? Sorry. MCQ number 4, which of the following changes will not affect the value of Pearson's correlation coefficient? Adding a constant to all the X values, multiplying all Y values by a negative number, swapping X and Y values, adding an outlier far from the trend, or adding a constant variable at Y intercept. Intercept is basically the same equation which was marked as lines and on which we are going to draw a tangent.
D.
Yeah. Basically, answer is A, adding a constant to all the X values so that we can interpret the Y values XY or XX. So MCQ number 5, in a data set with outliers, the student calculates a Pearson correlation of R is equal to 0.90. After removing the outlier, the correlation drops to R is equal to 0.45. What does this indicate? The outlier was hiding a strong relationship. The original data had no relationship. The outlier was inflating the strength of the relationship. Pearson's correlation increases with a fewer data points. The relationship can't be interpreted.
C.
C.
Yes, the answer is C. The outlier was inflating the strength of the relationship. So as we removed it, it would have dropped to 0.45, which is not that strong. MCQ number 6, a student calculates Pearson's correlation between height and shoe size using a sample of 50 people. They get R is equal to 0.65. Which of the following interpretation is most appropriate? Taller people always have larger shoes. Shoe size and height are unrelated. There is moderate positive linear relationship. Shoe size can be perfectly predicted by height, or shoe size is always following an upward trend.
C. Moderate
There
positive.
is a moderate positive linear relationship as 50 people are getting an R of 0.65. Height and shoe size. So you are asked to compute Pearson's correlation on data measured on an ordinal scale. What is the best approach?
A.
Pearson's correlation as usual. Convert data. Ji madam, the answer would be C. Use the Spearman's rank correlation coefficient instead, which we have discussed in some slides where Shapiro's test was also discussed. MCQ number 8, you calculate a Pearson's correlation of R is equal to 1.0 between two variables. What is the most likely shape of the scatter plot? Points scattered randomly, a perfect upward straight line, a perfect downward curve, a bell-shaped distribution, or skew to the right?
Beta.
B.
Answer is a perfect upward straight line. MCQ number 9, a study variable A and B have a Pearson's R. What percentage of variance
वो
in
दूसरा
C can
ट्रांसपोर्ट
be
वाली
explained by A?
सर
77%,
सेक्रेटरी के पास
51%,
डायरेक्टर के पास लेके जाना था
39%,
वो पूछ
or
रहे हैं उसका पूछे
0.47%.
उसको क्यों वो कल साइन की डॉक्टर ने दे दिया था
Any ideas for this very calculation? This is a solution because R square is equal to 0.78 square, which is basically the value given here. So it comes out to be 0.6084, which is equal to 60.84%. So the right answer would be B, 61% paid off to. So MCQ number 10, which scenario is most appropriate for applying Pearson's correlation? Checking if salaries, categories, and education levels are related. Investing the linear relationship between the temperature and ice cream sales, comparing medians of test scores across groups, examining how often two brands are purchased together, which brand shows least customer satisfaction. Okay, in all of the scenarios that we have also done in our marketing tab, investing the linear relationship between temperature and ice cream sales is basically the Pearson's correlation perfect scenario to be discussed in the values of R. So this is the key for our MCQs for your current users. And thank you very much for joining me. This is the link to our YouTube channel. Please do follow us